Hi everyone, so today we're going to be talking about link performance tips, and it's video 1 in a series of videos. I've touched on a link before, so I made a video about performance problems in links a couple of days ago, but I obviously have more material to show you, so we're going to get back to that video because there's some things that I haven't shown and I wanted to show you now. But let's jump in. So today we're going to be talking about link in general, so we're going to talk about a couple of interesting things. So first, it's the let keyword in link. Then we're gonna move to a group by operator, and then we're gonna touch on closures in general and in link. And we're gonna go back to that, circle back to that video that I made a couple of days ago about link. And I'm going to show you how closures are generated in that example. Okay, so moving on. Let's just say, for the sake of argument now, that we have something that's called a transaction, and that transaction has a single field in it called name. So we have a list of transactions, and we have two arrays which filter out these transactions. So we have an array of domestic transactions, and we have an array of foreign transactions. So our task here is to filter out transactions that are on one of these two lists. So the rest is going to be filtered out, and these will just remain. Okay, so as you might probably saw, these are lowercase names and these are like mixed case, but in this example they're all uppercase. So, in your typical link fashion, we would write something similar to this expression here. So, from X in transactions, where domestic transactions contains name to lower, or the foreign transactions contains name to lower, to list, and return the result. That's it. Simple expression and nothing really fishy going on here yet. Okay, so let's test the performance, and again, I'm not gonna use benchmark.net because for the sake of video it takes too long, so I've written my own measure function, which kind of works like benchmark.net. It will do all of sorts like these good things like the warm-up phase. It's going to run a couple of times, it's going to calculate the average, and this should be enough for the most cases. If you want, I can add like benchmark.net results into the description of the video, or maybe somewhere at the end. So this example takes 110 milliseconds. All right, but what we're doing here, so notice that we're doing name to lower twice because there's no way for us to be able to do it once, because we have to do it for every transaction. And sorry, turns out that there's a keyword for that where you can define a variable in link and then use that variable. So that's called a let. So here we have the same example where we're going to use the let keyword. So we're going to define a variable called n, and we're going to assign that name to lower. And then we're just going to use that n. So what we effectively done is we decreased the number of operations by half in terms of these checks here. So because we're doing two lower ones and then we just check. So that should be better for performance, right? Well, yeah, but there's always but. Keep that in mind that what you write in link is not what you're gonna get. So this is just an expression that gets converted to some code, but you might be surprised that in order to solve this problem, the compiler has to go to great lengths and will generate code that you would not expect and yourself would never write. So if we would write this the plain way, we would probably never write such code as the compiler will generate. Whether that's good or bad is yet to be seen, and let's actually see the performance. So, example 2. The first one took 110 milliseconds. So this is already surprising because it takes longer, 137 milliseconds. And it's even slower the second times we sort of run it, right? So it's around 20% worse, at least. So what's happening here, right? Like I said, what you see is not what you get in LINQ, and you have to be careful and you have to know that, because what this will generate is it will actually do, first of all, it's going to select. So it's going to transform each transaction to a new object, not a new variable. It's going to be a new object completely. That's one of the things. The second bit is that this new object will be captured in a new lambda, where it will still do like to_lower and stuff like that, and it's going to be very slow. And it's going to probably do things that I'm not even aware about, because this is just so big. So let me actually show you what the C# code compiler generated, because that's really interesting. So let's go to this tool where you want to check whatever you want to check what the compiler generates. You can go to ILSpy and decompile the code, and you're gonna see what's up. So this is our first example. So we're gonna do where transactions, we're gonna do the function, and we're gonna just do the lower. And it's, short. And this is the LED version. So this is the LED version here. It's pretty long and it's pretty surprising. So let's, I've actually copied it to the C# code, and as you can tell, it does the select, it does the filtering, and it does the select again, and then it will create a bunch of delegates, like one with to_lower, one delegate, another delegate, yet another delegate. Yeah, so it's bananas basically. So it's completely insane, and there's probably a reason why it has to be solved like that, but I kind of get the feeling that you could do better. All right, so how to solve this problem, right? So stick with this here. So stick with the simplest LINQ expressions that you can find, even if it has like duplicated code, because it might not get duplicated actually. So it's something to think about. You have to decompile and see the C# generated code, unfortunately, to understand some of these problems, but that's how it is. And if we wanted to go even faster, so if we wanted to actually cache that that value here, well, we could not do LINQ, for example, if performance is key. If it's not, then stick with this. But if it is, then let's just write a simple version of this expression. So we're just going to have a loop. We're going to take our transaction. We're going to do name to_lower. And then we're just going to check in an if expression. And lastly, we're going to add to the resulting list. And that's it. So that's all it takes to solve this problem. So let's see how the version 3 performs with just a loop. Well, it's at least 2 times faster. So it's 2 times faster from the first version and 2.5 times faster from the second version, which uses the LINQ expression. So that's pretty good. Yeah. So this is one of the pitfalls that you fall in when you're using LINQ expressions, and LINQ is not all bad. So, but you have to be very careful how you use it, and there's some pitfalls like this. So this example probably is a-okay if you're trying to use that, but this is not. But while we're at it, can we do even better than this version? Turns out, yes, we can. So there's a 4 version here that is faster, but what it does is surprising because it just changes the conditions. So now we're looking at foreign transactions, and then we're looking at domestic transactions. And this is sort of cheating, because if you know the business context, that you have more foreign transactions than domestic transactions, then you can be thoughtful about your if statements, and if you do, it's going to get even faster. So you have to measure this and have statistics and data that back it up. But if you do, then you can go a bit faster. It's like a couple of milliseconds, but you know, still. Okay, so as it turns out, you have to be careful with using link. But let's move on because there's some other things that I wanted to show you. So for example, there's this, well, this thing that you have to be careful about as well. So if we have a list of transactions and we're gonna do transactions last and measure the performance of getting the last item, it's gonna be 1.1 milliseconds. But if we increase this a bit and run it again, probably too much. Yeah, so too much. Let's leave it at 2 zeros extra. No, still? Okay. So now it's 154 milliseconds. That's something that we can sort of measure. And this is a list, right? So the last should be like instant. It shouldn't take any time. But since LINQ doesn't have the notion of type systems, it just has like interfaces, and all of the things are like based on IEnumerable, there's a couple of things that are happening here. So first of all of the calls will be virtual calls, which already takes adds just a bit of overhead on top, but that's not important. The important bit is that it doesn't know that it's dealing with the list, because if it did know that it's dealing with the list, we just could get the last element easily. So let's see. And LINQ can totally do it, because you can have checks to check if your IEnumerable interface can be converted to a list, and if it can, cast it much rather to the list, and if it can, then you can do it. But for some reason they don't. So let's write a function that will get our last element. So it's this function. Let's assign something to it, var x, and let's run it. So it's 13 milliseconds. It's 10 times faster at least. So for some reason the C# devs didn't include that. I'm sure there's a valid reason for that, or maybe there's just time. But it's something you have to be careful about when you're using LINQ, because it has all of these operators that can bite you. But we could, for example, implement this operator ourselves, because as it turns out, you can, in fact, override the default LINQ implementation, because if you have this included in your project in the same namespace, and you have this thing here, then it's going to use your implementation of the last. And if that happens, then we're just gonna use this implementation here, and as you can see, this is the default implementation of the LINQ, but we're checking against our iList, and if we find the iList, then we're just gonna do the same thing that I did. So if we're dealing with these sorts of situations, then we can easily replace the implementation of the last operator. So for example, if I know that I'm even dealing with an iList on a source, then I can already do it. And now if I'm gonna do the last, it's already faster, right? It's not as fast for some reason, because we have a bunch of more checks, maybe, I don't know, something, but it's faster already. So this check so actually there's no checks, but this is an iList, so it's a virtual interface. It's not our own, so perhaps there's some cost associated to that. Okay, so we can override all of the LINQ operators. I do not encourage you to do it. I just encourage you to override some of the implementation of LINQ if you feel that it's bad for you for some reason. But let's actually now talk about the good things of LINQ, because there's totally a bunch of good things in LINQ. So let's switch to example number 3. And again, the same thing, transactions, but this time around we have a different task. So our task is to group by the transaction, and we only want to return transactions that have the same name appeared on that list more than once. So in this example, we have two transactions that have a count of greater than 1. So we should just return this. So we're going to do a group by using LINQ. And let's see, so this is the group by. We're going to group by into names where names count greater than 1 here. And we're just going to select the names. And let's run it. 18 milliseconds, pretty good. Okay, so let's just say that we don't trust LINQ. We say that, yeah, we can do better. Let's try to do better by having a dictionary, which we'll use to count all of these things. And then we're just gonna go through the dictionary and add all of the key values, much rather keys that are greater than 1. They have a count greater than 1. So this is the dictionary version. It's what most people would do when they would try to re-implement this. Okay. Turns out it's a lot slower. How much slower? 2 times, 2.5 times? Something like that, 2.5 times slower. So as you can see, there's there's good parts about LINQ, and you cannot implement this really faster because the implementation of group by uses something that's called a lookup table. So this is like a data structure that they've built, and this data structure is extremely robust. So you just cannot, well, you can, but you have to try hard to implement a performant version of that. So there's just no point in doing that because in this example, LINQ actually wins, and it wins by a lot. But let's say that we're stubborn and we want to prove that we can do it. So we're going to implement our custom lookup, which we think is going to be faster. And let's see how that works. So we have basically a hash table. We're going to calculate the hash. This is here to not have minus values because get hash code can give you from minus x to plus x, and this and here will just flip that last bit, and it's going to be all positive values. Then we're going to have buckets, which we call groups, and we're going to add to group. So this is using a bunch of like clever stuff to be able to do it quickly. There's almost no if statement, so branches are eliminated, and it's all good, and it's all pretty good. As you can see, it's using inlining and a bunch of stuff. And let's try and, let's actually see how it performs. Because you have to just take my word for it, but this is an optimized data structure. It's not like dumb data structure. So it still takes, so it takes 26 milliseconds. While the first version of LINQ takes 14 when all of the caches are like optimized and stuff. That's why I'm running a couple of times, because the caches get hot and you can see the most optimal version, the most performant version much rather. So as you can probably tell, my version of the data structure, while optimized, is still slow as compared to the LINQ version. So I would have to do a bunch of other stuff here to be able to make it faster. So for example, I would need to use like a linked list here to like filter the nulls out of that group. Then I could have a much more optimized hash code implementation because this is not like a non-deterministic version. All of the deterministic versions would be faster. But like I said, it's difficult to do. So there's no point in, unless you're like have a valid use case, there's no point in implementing group by your own. LINQ is just better. So as we can see, LINQ is not all bad. So LINQ is good as well. And you just have to know where to use these things. So yeah. And lastly, let me show you a thing about closure. So in order to get this, you would have to probably watch my previous video. But let's see here. So I previously we had this find function written in LINQ where we had the where operator. Let me actually show you real quick. So we have this find function here, or we have this where operator, and I know we can do like, for example, this. We can remove that and we can add this here, but it was just to show you that people make this mistake all the time. So they do where something something and then first or default, and this is like a redundant call. It doesn't have to be here. You could just do first or default and pass that lambda in here, but this has all sorts of problems. So first of all, this is enumerable. And again, virtual calls already, this is on the list under the hood, but we don't know. So we're gonna promote our iterator to the heap. We're gonna get this item, push it to the heap. We're gonna get this lambda abstraction, push it to the heap, and there's gonna be a bunch of allocations that we didn't even want to have. And why is that happening here? Because some of the lambdas don't have to be promoted to the heap at all. But when you have a situation like here where you just pass something inside of the lambda from some inside context, then it has to be promoted to the heap, because wherever you run this, it has to be in a public class where this guy can reach it. And this code here shows you how it's implemented. So this is our find function where we have our first or default, and we have this display class here which we're going to initialize, and this item here that we're interested in because it's used in the where expression is going to be hooked to this field of this display class. And now our condition is going to be presented as a function here, which returns a bool, and we're gonna use this here, and that's why in this example we're actually boxing the item and the lambda and everything else, because like I said, it doesn't have to be like that, but here there's just no choice. So how would we solve this problem? And this is a discussion for like a series of videos, I guess, because it's tied to compiler and compiler designs. You would have to effectively bake that value. So what I mean by that, so when you passing this along, you create a copy of it inside of this LINQ method, and you just use that copy, and then that lambda doesn't have to reach anything anywhere else because the value is effectively baked. So the compiler could even turn it into a static at this point of invocation. So for example, if this is 10, the compiler could just do greater than 10, and now there's no problem, because if this is greater than 10, then we don't have to create all of these classes and do all sorts of these weird things. We can sort of verify that the compiler does this, because I'm not sure if it does, but if this would be baked, so baking means like evaluating the variable and caching it in somewhere. Is it here or just turning it into a const? That will be fine as well. Then there's no problem. But then you have to throw the value array, but it's possible. So it's possible to create a compiler like that to be able to do these things. And maybe we're going to see it at some point in .NET as well. So let's compile this. Let's throw this guy away because it does not refresh automatically. And let's add this. And let's see now. So we still have a class which is sealed, but now we don't have any sort of variable. So that variable is not going to get promoted to the heap, but still that function is going to be promoted to the heap. And that's not optimal still, but we could still probably, I mean the compiler, could probably skip generating this class altogether, because if we're gonna have a function, then we could probably use something like a local function here. So there's ways to do it, but it just is out of the scope of this, you know, video at least. So that's all for today. So thanks for watching. If you have questions, leave them like in the comments. If you like the video, leave a thumbs up, and thanks for watching. So yes, bye.